All right, this is video number 3 for section 6.6. Solving logarithmic equations now. A logarithmic equation is an equation where the variable is inside of a logarithm. So for example, log of 3x equals 10, or natural log of z minus 1 plus natural log of 7 equals natural log of 1 over z. The variables are inside the logarithms. Just like how we used logs to solve exponents, we're going to use exponential form to solve logs. Remember, you must always check your solutions, especially with logs, because sometimes they bring in solutions that aren't in the correct domain. Let's do an example. We're going to start, here's a straightforward example. We're going to solve this equation, logarithmic equation, by switching it to its exponential form. So we have log base 10, because there's nothing written, so it's base 10 of z minus 7 equals 2. The exponential form would be 10 to the 2 equals z minus 7. 10 to the 2 equals z minus 7. This says 100 equals z minus 7. Add 7 to each side, and 107 equals z. That's our solution. We check it. That log of 107 minus 7 equals 2, question mark. Well, that's log of 100. And sure enough, that does equal 2 because 10 squared is 100. Check. Let's try a little bit harder example. All right, here's our next example. Just like with exponential equations, we need to isolate the log before we switch it to exponential form. So the first thing we're going to do on this one is we're going to divide both sides by 6. This becomes a natural log of 2x, and this becomes 5. Now we rewrite it in exponential form. Remember, the base is e for natural log. E to the 5 equals 2x. And we're just going to leave that as e to the 5. Remember, e is just a number. And if we put it in our calculators, we can get a decimal approximation, but it's more accurate to just leave it written as e. Simply divide each side now by 2, and we get x equals e to the 5th over 2. That's our final exact answer. To check it, we're going to plug it back in. You can get a decimal and plug it back in if you want to, but this one actually works out pretty nice if you just plug it in. 6 times the natural log of 2 times our x value, which is e to the 5 over 2, is this equal to 30? Well, e to the 5 over 2 times 2 would just be e to the 5. 6 times the natural log of e to the 5. What is this equal to? Is it 30? Well, the natural log of e to the 5 is asking what power we put on e to get to e to the 5. So this must be equal to 5. 6 times 5 is 30. Check. Let's try another logarithmic equation. Sometimes we have to use property of logs. When you're solving logarithmic equations, you always want to get it to a single logarithm and then switch it to exponential form, a single isolated logarithm. So we're going to use our log properties to get this to a single logarithm, and then we're going to switch it to exponential form. So the first thing we're going to do is we're going to add log 4 to each side. That gives me log of y minus 1 plus log of 4 equals 5. Now I can use the multiplication addition property of logs. Remember, that property says log of a plus log of b equals log of a times b. We practiced these in the last section. So we have log of a plus log of b, so this becomes log of y minus 1 times 4. Now we have an isolated single logarithm. We can switch it to exponential form. 10 is the base, so 10 to the 5th equals y minus 1 times 4. 10 to the 5th is 1 with 5 zeros. So 100,000 equals y minus 1 times 4. Divide both sides by 4. 25,000 equals y minus 1. Add 1 to each side. And my solution is y equals 25,001. Let's check our answers. Do it over here, check. If we take log of 25,001 minus 1, is that equal to 5 minus log 4? And use our calculators to get some approximations to check this. So let's take the log of 25,000 and 1 minus 1, which gives me about 4.398. Is this equal to 5 minus log 4, which is about equal to 4.398. So check, we got the correct answer on that one. All right, let's try this again. This one requires us to use the division subtraction property. Why don't you pause the video and give this one a try on your own? All right, hopefully that went well. Let's review the property. The property is log of A minus log of B equals log of A over B. Applying that to this problem gives me log of t plus 2 over t minus 1 equals 1. Now we have a single logarithm. We can switch it to exponential form. Again, we're base 10. 10 to the 1 equals t plus 2 over t minus 1. That's starting to look like 12. All right, this is a rational equation. We know how to solve these. We're going to multiply both sides by t minus 1. This is 10t plus 10 equals t plus 2. Get the t's to one side. Oh, that was minus 1. So 10t minus 10. Sorry. Add 10 to each side. That gives me 9t equals 12. Divide by 9. T equals 4/3. That's my exact solution. Let's check it. Log 4/3 plus 2 plus log of 4/3 minus 1. We hope this equals 1. Let's plug it into our calculators and check. Log 4/3 plus 2 plus log 4/3 minus 1. And I get that's equal to, wait a minute, I did something weird. I got it's equal to 0.045. Let me try that again. I don't think I punched that in correct. Let's do log 4/3 plus 2. I got 0.523. And we're going to, subtract it. That might be a difference. Subtract minus. Now let's plug in log of 4/3 minus 1. And I get negative 4.77. If I add these guys, because subtracting a negative is the same as adding, add to that 0.523. And sure enough, I get pretty close to 1. Close enough to 1. Check. All right. So one more example? I think there is. I think this is the last one. Oh, nope, we have 2 more. This is a longer section than I remember. Oh, yeah. All right, let's go ahead and get started on this one. This time there's 3 logarithms, so we're going to have to use the property of logs that, so we can combine these. This is the addition property, so let's go ahead and use that one first. Natural log of v times v minus 7 equals the natural log of 5v. And now actually, since we have a single logarithm on each side, we can use the fact, much like with exponents, that since logs are 1 to 1, so since logs are 1 to 1, we know that if log A equals log B, that implies that A equals B. So right at this point, we know that we can set v times v minus 7 equal to 5v. All right, let's try to solve this. V squared minus 7v, multiplying that out, equals 5v. Does this look familiar? It's a quadratic equation, right? How do we solve quadratic equations? Well, there's a couple different ways. One thing we do is we set it equal to 0 and use the quadratic formula, or we set it equal to 0, use the 0 product property, and factor it. So let's set it equal to 0 by subtracting 5v from each side. So that gives me v squared minus 12v equals 0. This one looks very factorable to me. Let's pull out a v. V minus 12 equals 0, so v either equals 0 or v equals 12. Let's check these solutions. Lots of times when you're doing logs and end up solving a quadratic equation, what can happen is you get an extraneous solution. All right, let's take a look. Natural log of 0 plus natural log of 0 minus 7. I think you guys could already tell that this 0 is going to be a problem. So these are my solutions. The 0 is going to be a problem already because we can't take the natural log of 0. And we can't take the natural log of 0 minus 7. There's really no point in even continuing because we know this guy is not in the domain. So that one is not going to work. Let's try 12. Natural log of 12 plus natural log of 5. Is this equal to the natural log of 5 times 12? You're welcome to use your calculators to get decimal approximations for this, but I know this is already true because I know properties of logs. Natural log of 12 plus natural log of 5 is equal to natural log of 12 times 5, which is exactly what I have. Natural log of 60 on both sides. So check. So this is one time when you have to check for extraneous solutions. Let's do one more example of this. All right, let's solve this one together. So we have to use the addition multiplication property of logs. This becomes log of t plus 2. Oh, that's not even close to a 2. Times t minus 1 equals 1. Now we have it as a single logarithm, isolated. We can switch it to exponential form. 10 is my base, so 10 to the 1 equals t plus 2 times t minus 1. Many people at this point are tempted to just factor right now and say, oh, my answers are negative 2 and 1. But remember, it's the 0 product property, not the 10 product property. That only works when you're multiplying to something that equals 0, not two things have to be 10. One of them has to be 10 if you're multiplying to 10. So that does not work. We have to multiply this out and then set it equal to 0. So 10 equals t squared minus t plus 2t, excuse me, minus 2. 10 equals t squared plus t minus 2. Subtract 10 from each side, so we set it equal to 0. 0 equals t squared plus t minus 12. We could use the quadratic formula at this point if you wanted to. I'm going to factor because I can see the factors. 0 is t plus 4, t minus 3. T squared minus 3t, that works out. So my answers are either equal to negative 4 or positive 3. Those are my solutions. Let's check both of them in the original equation. So log of negative 4 plus 2 plus log negative 4 minus 1. I think we can already see this is going to not work because this is going to become log of negative 2. That's no good. That guy is not a solution. Negative numbers are not in the domain of log. Let's try the 3. Log of 3 plus 2 plus log of 3 minus 1. Is this equal to 1? Well, this is going to be log of 5 plus log of 2. Is this equal to 1? Well, this is log of 5 times 2, which is 10. And log of 10 is equal to 1 because 10 to the 1 is 10. Check. And that's my solution. All right, that's the end of this video.